Okay, now we will begin the 4.3, which is reflection. This is something we have learned in our lower classes, that reflection occurs. Reflection basically occurs in light when the ray of light bounces back to same medium, right? We all know that. We also know the law of reflection. The law of reflection, in mirrors we have done them, and that states that angle of incidence is equal to angle of reflection. Okay, and we also know other things like, so if there is a mirror here and then you have a normal here, which is your normal N, and then you have an incident light which is coming here and then it gets reflected, so you have your I, you have your R, this is the incident, this is the reflector. So this is the incident ray and this is your reflected ray and the normal. Okay, so now reflection also occurs in case of wavefronts. So if I talk of reflection, then of wavefront also occur in similar way. Okay, so if you have a mirror, polished mirror, and then you have your ray of light coming, and then you have a normal, it goes off, which means it just goes off. See, just goes off, and your I is equal to your R. Okay, now come to reflection of pulses. Let us understand this now. Reflection of pulses, what does it mean? It simply means that if I have a fixed rope, this is a fixed rope, okay, this is a rope, and I vibrate the rope up and down so that it generates a wave which goes and then strikes here at the fixed junction. See, now according to Newton's third law, every action is equal and opposite reaction, and because the rope is tied here, so it will just simply come back. I can't use another color, I'm sorry, otherwise it would have been more clear actually. Okay, so this is how your wave actually reflects back. Now let us see it in a very simple way. Let us understand a very simple way. Okay, so a wave comes, this is your wave, that crest strikes here, and how do you show the return one? It simply goes this way and then goes off. Okay, so it comes this way but then it leaves this way. Now Newton's third law is applicable. So reaction causes the reflection. But there is another case here. There's a special case also. There's so many special cases actually. I'm just discussing few. Special case here. That is, what if that rope which was here initially is no more fixed here, is just tied with a ring. This is a ring, and the ring can move up and down. See, the ring can move up and down. Now what do you think will happen? So the wave comes, let's draw it here. Okay, the wave comes like this, and the ring, okay, it comes this way. The ring moves, and then what happens is you still get another wave but there is no difference here, something like this only, but then it goes back this way. See, do you understand the difference here? So if it is fixed here, the Newton's law is applied and then it comes back. See, it bounces in the other side. Okay, reverses out. But in this case, it remains crest only. Alright, so this is the difference, one of the differences that we see. Now, let's say another case, another special case. What happens if my first rope is thin, whereas my second rope is thick? You see, this is very thick rope. Then what happens now? So my pulse is coming like this, okay, and then it's not yet straight, so it will come to this point, and when it comes to this point, when it reaches here, at that moment for him this is like a fixed point, so a bit of it will reflect back like this, and something of that will also go in that thick one. See, like this. Okay, so this is something that we need to understand. Anyway, now these are reflection, and we can have these questions in many ways. Another case could be something like this. Okay, let's not discuss that now, we'll discuss a little later, because when we do superposition I think we will discuss that part. So let us now go to next concept, that is refraction. So what exactly happens in refraction now? When does refraction basically occur? We all know that when a ray of light travels from one medium to another, from one medium to another, the speed decreases, and now the speed decreases under what condition? Decreases if density increases, right? So that was refraction, and if you recall in your our lower classes we have all studied something like this. You know, this is the way light bends and then it goes off, and then if you pull it back you get lateral displacement here parallel, and you get your I, you get your R, you get your E here, all those things. And speed of light here in air is approximately 3 into 10 power 8, and inside the glass it is speed of light is 2 into 10 power 8. And then if you remember, you found the refractive index by speed of light in air by speed of light in glass. All those things we did, and then we used to get the answer to be as 1.5. okay, now in this case we are talking about the refraction of a wavefront. Now wavefront behaves little differently. See, the wavefront basically, if this is the line where the mediums are separated, and let us say this is rarer medium and this is denser medium, okay. Now the wavefronts are arriving, so one, and then let's say another one, and then say let's say another one, and then let's say another one, okay. Now what exactly happens is, here the speed is greater because this is denser, so speed is less, okay. And then these rays of light which have reached the surface are having a wavefront, something like this, see, right? And these wavefronts behave very interestingly, and there are wavefronts here, there are wavefronts here, see. If the speed decreases, then the wavefronts are found to be compressing themselves, so they start compressing, something like this, something like this, see, something like this. So actually they compress, and then they compress. This is how they behave then, see, they got compressed now. Now what happens? The wavefronts get compressed in denser medium. That makes logical sense also, because there are more particles there, but there is not enough energy by the incoming wavefront to distribute to so many particles. So maybe that is one of the reasons why the wavefronts get compressed. By compression here I mean that wavelength decreases, and we know very well that V is equal to F lambda. F does not change, so if lambda decreases, then speed also decreases. Of course, this works very fine here. And if you give an example, let's say give an example, waves moving from deep waters to shallow water, the waves or wavefront get compressed. So the wavelength lambda decreases, right? And that is the case what you are seeing here. Then it becomes something like this. Imagine if this is like, you know, your deep water, and this is like your shallow water. This is exactly what happens. But you can apply these formulae here, the Snell's law. If you remember the Snell's law, we used to write as Snell's law, we used to write as sine I by sine R, isn't it? Okay. So this is the end of reflection and diffraction of the wavefront and general idea that we have already studied in the lower classes. And we'll discuss more in further total internal reflection and other concepts. Okay, thank you.